Good morning, everyone. So today we have a plan to discuss an activity scheduling problem, which actually uses greedy strategy. So that's why you have given the heading of this discussion, activity scheduling problem using greedy method. So let me tell you what we have been given actually. We have been given a set of activities. And our objective is very clear from the name of the problem. That means we have to schedule the set of activities. So normally an activity maintains two parameters. First of all, the first parameter is called the starting time of that activity. And the second parameter is called finishing time of that activity. And our basic objective is to schedule those given activities by maintaining some condition. So let us now focus the activity scheduling problem along with its objective, a sample numericals, and finally derive the algorithm and analyze the complexity step by step. So let us move on for the board work. So let me proceed further to the next slide. Okay. So now, before proceeding to that one, let us now talk about what an activity scheduling problem actually is. In activity scheduling problem, we have to determine the optimum number of activities actually. And we have to determine the optimum number of activities that are scheduled to the resources. That's why it is called activity scheduling problem. Suppose we have been given a set of activities. Suppose we have been given a set of activities. Let me proceed to the next slide. Suppose we have been given a set of activities. Suppose it is S. And the activities are numbered as activity 1, activity 2, activity 3, up to activity N. Okay. So we can say that we have been given a set of activities capital S consists of N number of activities. Each is scheduled to use some resource where each condition might arise where multiple activity has its start and finish time denoted by, suppose, SI, starting time of an activity I, and FI respectively, which actually calls the finishing time of the activity. And activity number I. A condition might arise where multiple activities are scheduled to have a common resource, or we can say that the start or finish time of the activities may overlap. From the given set of activities, we can say that activity AI, that is ith activity, and activity AJ, that is another activity which is called jth activity, are non-interfering activities if and only if they both have different start and finish times. That means their start and finish time do not overlap. That is, if the starting time of AI is SI and finishing time of AI is FI, and if the starting time of AJ is SJ and finishing time of AJ is FJ, then we can say that they are called non-interfering if AI intersection AJ equals to 5. Okay, so they should have different start and finish time. Okay, the activity scheduling problem actually is to select a maximum possible set of activities where each activity is non-interfering. This statement is very vital. This statement is very, very vital. The activity scheduling problem is to select, let me write in brief, activity scheduling problem is to select, let us write it, is to select a maximum, we can say that, is to select a maximum possible set of activities maximum possible set of activities where each activity is non-interfering. Each activity is non-interfering. That means they do not overlap. Let me go back to the previous slide. So we have to select maximum possible set of activities where each activity is actually non-interfering. So what may be the solutions of this problem? One possible method to select the activity is to first choose that activity which has maximum start and finish time. Somebody may propose it, but it seems to be time consuming as this activity holds the resource for the longer time, because somebody who has given this proposal, he or she has said one possible method to select the activity is to first choose that activity which has maximum start and finish time. I told this problem is solved using greedy strategy, so different proposals may come out. So one possible proposal which we are currently discussing is to select the activity, is to first to choose that activity which has maximum start and finish time. But again, I'm telling, it seems to be time consuming as this activity holds the resource for the longer time. And the discussion leads to the greedy strategy, there is no doubt. And according to this, we have to select repeatedly the activity which has maximum duration. And what is the duration formula? Duration is nothing but Fi minus Si, finishing time of the ith activity minus starting time of the ith activity. This is actually called the duration, and schedule it such that it does not interfere with any pre-scheduled activities. But this technique also seems to be somewhat non-optimal. So the first proposal, which has come out from any one of the corners, it is now being rejected. Here, we are giving the greedy strategy which provides the optimum result. And what is that? The idea behind this strategy is same as we are discarding that activity which has longer duration. That means Fi minus Si value is too large. And in this strategy, we first select the activity with minimum duration. That means the difference between Fi and Si should be minimum, and then we schedule it. That means the strategy which we are going to implement now as the solution, in this strategy, we first select the activity with minimum duration and schedule it. Next, we escape all activities that interfere with this one. That means we have to select non-interfering activity having minimum duration, and then we have to schedule it, and the process is repeated until all activities are considered. So from the previous proposal, which was given as we have to select the activity which has the maximum duration stands cancelled, now we are just implementing the opposite concept where we are scheduling the activity which has minimum duration, and the process is repeated until all activities are considered. And it can be observed that the process of selecting the activity, this is very vital. It can be observed that the process of selecting the activity becomes faster if we assume that the activities are arranged in an increasing order of their finishing time. So 2 points are very vital. We are going to select the activity which is of having minimum duration, and it is observed that the process of selecting the activity becomes more faster if we assume that the activities are arranged in an increasing order of their finishing time. That means we can represent F1, that is activity 1's finishing time, A1 is chosen if and only if its finishing time is lesser than or equals to F2, lesser equals to F3, lesser equals to dot 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 f of n in this manner. That means increasing order of their finishing time. Okay, so this proposal is now accepted. We are going to select the activity based on their minimum duration, and it is already proven that the process of selecting activity becomes more faster if we assume that the activities are arranged in an increasing order of their finishing time. So the method is very simple. We have been given a series of activities. Our objective is to schedule those activities, and not only the scheduling is our priority, but also we have to have this objective that as many activities we can cover in the schedule so that no two activities are interfering each other. That means they should have different starting and finishing time. It is expected. One proposal was rejected because somebody has given this proposal where they are selecting the activity based on the longest duration of the activity, but it is more time consuming. Later on, we have taken the opposite proposal. We are going to select the activities. They have the minimum duration, and one proposal is added to select the activities more faster way based on their arrangement in the increasing order of their finishing time. So these two are very important. So let us first solve one very simple numerical, and from that numerical we are going to understand what is actually happening behind it. And if anybody can solve this numerical, they can usually understand what is the proposal which is accepted, and from the solution of those numerical anybody can easily implement the algorithm. So let us go for the second slide, and let's take one example. Suppose we have altogether 10 activities and they are numbered as A1, A2, A3, A4, A5, A6, A7, A8, A9, and A10. Very good. I told at the beginning of this discussion that each and every activity maintains two parameters. One is the starting time and another one is the finishing time. So let us maintain it. Suppose the starting time of first activity is 1 and its finishing time is say 5. Okay. Suppose activity 2 has the starting time 2 and assume that its finishing time is 3. Suppose activity 3 has the starting time 3 and finishing time is 4. Activity 4 has the starting time 4 and its finishing time, suppose it is 6. Activity 5 has the starting time 5. It is somehow matching with the index of the activity, and suppose its finishing time is 7. So it is as usual 6, it is 7, it is 8, it is 9, it is 10. Let us complete the finishing time of from A6 up to A10. A6 finishing time is, suppose it is 8. Very good. Now suppose it is 11 for A7. For A8, suppose it is 10. For A9, suppose it is 12. And yeah, for A10, suppose it is 13. I told you that we have to select the activities, or we can say that the process of selecting the activity becomes faster if we assume that the activities are arranged in an increasing order of their finishing time. So let us make an arrangement. That means we have to arrange the activities in increasing order of their finishing time. This is our first job. So let us arrange it. So this is our data set. So let us go for the pre-processing. So activity 2 is of having finishing time 3, which is less. So activity 2 should be selected first. So A2, it has the starting time 2 and ending time is 3. So next, it is very simple to understand that activity 4, it is easily located that activity 3 is of having the next smallest finishing time. So after A2, A3 will come. Okay. So this is just the arrangement of the activities based on their increasing order of their finishing time. Very good. Then definitely A1 comes. So it is 1, 5. This is the main priority based on which we are arranging the activities. Then A4, 4, 6. We just notice it 3, 4, 5, 6. Okay, then A5 is coming. Yes, it is definitely 5 and it is 7. Then yes, A6 is coming. It is 6, 8. Then A8 is coming. A8, because its starting time is 8, but the ending time is 10. After 8, the next minimum is 10. Increasing order. Then yeah, A7 is coming. It is 7, 11. Yeah, then A9 is coming. It is 9, 12. Then A10 is coming. It is 10 and 13. So this is the actual arrangement. We consider this one for further processing. So after arrangement, A2 will come first, then A3, then A1, then A4, then A5, then A6, then A8, then A7, then A9, and then A10. This is the parameter to arrange the activities based on the increasing order of their finishing time. Then first of all 3, then 4. In this way, we have arranged the activities. So let us plot one graph-like structure by which we can show the scheduling sections. So suppose this is the way to plot the time along x-axis, and let us make a unit distance of arrangement here. 1, 2, then 3, then 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, suppose. Let us put the activity along y-axis and see what actually happens. So we have to consider A2 first. The starting time of A2 is 2 and finishing time of A2 is 3. So 2 to 3, this part is normally occupied by A2, 2 to 3. Okay. Then let us check whether A3 can come. A3 starting time is 3, where A2's finishing time is 3. So A3 we can consider. No issue, there will be no interfering. So after A2, we can take A3 and the slot is from 3 to 4. Okay, so there is no interference. So now A1 starts from 1 and ends at 5. So if I take A2, then A3, then how does A1 comes? Because if A1 comes, A1 wants to book the slot from 1 to 5, but there will be an interference of A1 along with A2 and A3. So if I take A2, then A3, then I cannot consider A1. I cannot consider A1 because A1 is interfering with A2 and A3. So A1 stands cancelled. Then I'll go for A4. Yeah, A4 I can take. Yes, A4, because A4 starts from 4 and ends at 6. So 4 to 6, this slot is booked by A4. So in this graph, I am only showing those activities which are non-interfering. I'm not showing all other activities. So here A1 is cancelled. Then I take A4. So A1 cancelled, A4 accepted. Then once A4 is accepted, I cannot consider A5 because A5 starts from 5, but A4 is continuing from A4 to 6. 5 is in between 4 and 6. So once A4 is in the slot or in the schedule rather, I cannot consider A5. There will be an interference. So A5 stands cancelled. So I can take A6 without any hesitation because A4 releases at 6. So I can take A5 without any interference. So A6 starts from 6 and ends at 8. So be careful. A6 also books 2 slots, 6 to 7, 7 to 8. Yes, I can take 8 because there is no doubt of no hesitation because A6 ends at 8. 8 should start from 8. No issue. A8. And it continues up to 10, up to 10. Okay. So 8 to 10 is booked. Very good. So it is very clear. The same logic using which I have discarded A1 and A5. The same logic is applicable for A7 because A7 starts at 7, but 7, this was already occupied by A6. So A7 cannot come. Now verify A9. A9 starts from 9 and ends at 12. It starts from 9, where 8 to 10, the entire slot is booked by A8. So once A8 is in the picture, A9 cannot come because there will be an interference with A8. So only A10, yes, A10 has the right to come because A8 releases it at 10. So I can consider A10. It starts from 10 and ends at 13. So these are all activities which are non-interfering. I have not shown A1 in the picture because A1 is interfering. I have not shown A5 in the diagram because A5 is also interfering. I'm not showing A7. A7 is also interfering, and I'm not showing A9, applying the same logic. So the activities which are in the final schedule are nothing but A2, then A3, yes, then yeah, A4, fine, then A6, fine, then A8, and last one, A10. So these are the series of activities which are non-interfering. They have been picked up based on their increasing order of their finishing time, expected that they have the smallest durations. They have been chosen up to maintain the faster progress. They have chosen based on their increasing order of their finishing time. And once A2 is placed, A3 can be placed because A2's duration is from 2 to 3. A3 can start from 3 and ends at 4. But A1 cannot come because there is an interference between A1 and A2 and A3 because A1 starting time is 1 and ends at 5. So 1 to 5 A1 occupies. But in between 1 to 5, 2 to 4 is occupied by A2 and A3. So definitely there is a collision between A1, A2 and A3, but there will be no interference between A2 and A3. So A2 and A3 is selected, A1 is cancelled. So in this way, you can select the activities. So altogether 1, 2, 3, 4, 5, 6. 6 activities are in the final schedule. So now it is the time to derive the algorithm. Algorithm is very simple to implement. Let us move on to the next slide. And to implement the algorithm is very simple to understand. So suppose that the name of the algorithm is activity dash schedule. Suppose this is the name of the algorithm. And here I have two parameters. One is capital S and another one is small f. And this function, that is activity schedule, actually computes the optimum set of activities. For determining the interferences, let us assume that we have another variable that we will introduce in the picture, that is name of the variable is pre, which actually holds the index of the recently scheduled activity at any time. So it actually holds the index of the recently scheduled activity at any time. It is very vital, at any time. Okay, and the start and finish time of the activities are denoted by and the start and finishing time of the activity is denoted by S and F respectively. Okay, fine. So these are the two parameters. One is the starting time, another one is the ending time, that is the S and F. Somebody might say that it is small s, small f, whatever the name of the parameter, that is dependent upon the designer, not an issue. So first step, that is step one, this is actually called initialization. So what is the initialization? Suppose we have a list or the array where we will store the activities which are scheduled. Suppose this is the activity set, and the name of the set is A list. Okay, and where I have taken the first activity, activity 1. Okay, then your question is, which one is the activity 1? So let us first move back to the previous slide. Here, these are the actual scenario, A1, A2, A3, A4 up to A10. These are the actual nomenclature of the activities. But once the processing is done, that means the sorting operation is done, before applying the verification of the interference between activities, before that we have made a sorting, and the sorting of activities before selection, and here the sorting is done based on their increasing order of the finishing time. So that's why A2, activity 2, had the smallest finishing time. That's why it has been shifted at the first. So basically A2 will be selected first. Then the next A3 is of having the next minimum finishing time. That means 3, then 4. In this order we have selected them. But once it is already arranged to the computer, A2, which was actually the second activity, it becomes the first activity to the computer. So A2 is actually the second activity, but to the computer, it is the first activity. Okay, to the computer, A3 is the second activity. Okay, to the computer, A1 is the third activity. Like we applied this type of concept when we deal with fractional knapsack problem. Once the items are arranged based on their ratio, that's the item selected first is of having the highest profit weight ratio, to the computer that item was the first item. Here also the same strategy is applied. A2 was actually the second item, but after sorting, A2 becomes the first item to the computer. A3 becomes the second item to the computer. So actually, whenever we are dealing with the algorithm, then this is one, that's the first activity. Actually, as per the example, it was A2. So the first activity, after sorting, that should be placed into the resultant. And resultant is nothing but the A list, where the final schedule will be preserved. Okay? And the index of the first activity is assumed to be 1. Index of the first activity is assumed to be 1. Though it was A2, its index was 2, but to the computer, it is actually the first activity, that is A1, so its index is 1. Again, I'm telling, after sorting, any one of the activities, either A2 or A3, depends upon the parameter, they may be the first activity. And after sorting, whatever may be the first activity, that will be selected as the first activity, and this will be treated as the first activity by the computer. So be careful, after arrangement, any one of the activities having different index other than 1 may be selected as the first one. Okay, and it is to the computer. Here we are implementing the algorithm, and the algorithm, based on the algorithm, we have to write the program code. So here, not only we are not solving the problem using pen and paper. Here, with the help of the computer, we have to implement the algorithm by applying some suitable program code. So we let the computer we understand which activity is actually the first activity to it. So after sorting, A2 becomes A1. After sorting, if you go back to the previous slide, after sorting, A2 becomes A1. After sorting, A3 becomes A2. After sorting, A1 becomes A3. In this way, computer maintains the activities. Okay. Though using pen and paper, it is very simple to pick up. Though using pen and paper, it is simple to manage. But you have to make the algorithm in such a way so that computer can understand which one is the first activity, which one is the second one, and which one is the third one. And it is assured that you will get the same result, though you are writing the algorithm to the computer. Okay, so let us move on. So as the first activity is selected and placed into the resultant set, and the first activity's index is also 1, so the parameter that I told pre holds the index of the recently scheduled activity. As the recently scheduled activity is 1, its index is also 1. So we have to keep the index of the currently scheduled activity into pre. So A list will maintain the set of activities 1, 2, 3, 4, and its index will be maintained under the variable pre, currently scheduled activity or recently scheduled activity. Okay. So now step 2 is very interesting. First activity is already scheduled. Now you have to check the remaining activities, whether the remaining activity after placing the first activity can be placed into the schedule or not by maintaining the condition that no two activities are interfering each other. So here we have to check it. So for the remaining activities, we have already scheduled first activity. We have altogether n activity. So we have to judge from second activity onwards. So definitely there is a implementation of the loop structure. So we have to pick up each activity once. We have to check the condition, and if this activity can be scheduled, we have to place it. Otherwise, we have to reject it. We have to go for the next activity, and we have to complete all activities present in the activity set, and we have to maintain the prepare the final schedule. As simple as that. So let us incorporate for I equals to 2 to n. 2 to n means from second activity up to the last activity you have to go for. So now I told you S and F indicates two parameters which are indicating the starting time and finishing time. Now, though it appears like two ordinary variables, but they are actually two one-dimensional array, because if you go back to the previous slide, you have two parameters. One is the starting time set and another one is the finishing time set. So it is basically array of starting time and it is basically array of finishing time. So S and F, though it looks like an ordinary variable, actually S holds the set of all starting times of the activity after sorting, and F holds the finishing time of all the activities after sorting. So in our example, this is actually S and this is actually F. S1 is 2, F1 is 3, S2 is 3, F2 is 4, S3 is 1, F3 is 5. In this way, we have to proceed further. So now come back. So let us verify that is starting time of the second activity which is expected to be scheduled, that may be scheduled, that may not be scheduled based upon the criteria. So we have to check if starting time of the current activity which is supposed to be scheduled, if it is allowed based on the criteria which is satisfied, starting time of the ith activity, if it is greater than or equals to finishing time of the previously scheduled activity or recently scheduled activity, finishing time of the recently scheduled activity, we can get the index of the recently scheduled activity by calling pre. So we'll just the parameter pass pre here. So f of pre actually indicates the finishing time of recently scheduled activity, which will be verified with starting time of the current activity, which is now the candidate activity, whether it is scheduled or not. So starting time of the second activity must be checked with the finishing time of the first activity. Starting time of the third activity needs to be checked with the finishing time of the second activity. In this way, we'll move on. Okay. So starting time of the ith activity, if it is greater than or equals to finishing time of the previous activity, then yes, they can be scheduled. They can be scheduled means ith activity is accepted. Then we have to append I, that is the activity number, to where? To a list, because a list is nothing but the array of activities that will finally display the final schedule, a list. Okay. And we have to update pre. So we have to set pre that will be updated with the recently scheduled activity, which is nothing but I. So in this way, loop will continue, and activity will be updated in the A list, and those activity will take place into A list which are non-interfering. And once the full process is complete, we finally return a list to show the final result. So this is what about activity scheduling problem algorithm. And this algorithm requirement is that the activities are sorted by their finishing time and nothing but the increasing order of their finishing time. And the running time of the algorithm is nothing but big theta of n log n, as sorting can be done in order of n log n time. And there are big O of one operation per activity. Thus, the total is order of n log n plus n into order of 1, because you have total n activities. So altogether, it is big O of n log n. So this is the complexity. So just for the time being, let us map with the previous example. As per this one, A2 becomes A1. So this is the first activity. So it is by default schedule. So its finishing time is 3. Okay. Now the second activity starting time is 3. So as per the algorithm, it is written S of I, that is actually 3, that is which is greater than or equals to f of pre, that is the previously scheduled activity, which is also 3 here. So we can say that 3 is greater or equals to 3. Yes, it is non-interfering. Then you can append second activity to the A list, and you have to select or update the index of the pre with the currently selected activity. So initially I pre was 1, now pre becomes 2. In this way, you can finally cover all activities in this manner. Okay, so this is what about activity scheduling problem using greedy strategy. Just for a summarize, you have been given a set of activities, and each and every activity maintains 2 parameters. One is the starting time and the finishing time. And the activity scheduling problem is to select maximum possible set of activities where each activity is non-interfering. As we have 2 parameters for each activity, finishing and starting time, so the duration formula is nothing but the difference between finishing time and the starting time, fi minus si, where I is the index of the ith activity. One proposal came to select the activity. The scheduling is to select the activity having maximum duration, but it is not at all a very good solution. And the other, it is time consuming. Another proposal finally accepted. You have to select the activities based on their minimum duration, and the selection of the activities become more faster if we assume that the activities are arranged in an increasing order of their finishing time. So whatever the data set are given, starting and finishing time of the activities must be there. We have to arrange the activities before scheduling in order of their increasing order of their finishing time. So it is not assured that the first activity, as per its own nomenclature, can become the first activity since beginning and up to the last. No, because here it is seen that A2, which was the second activity, actually it became the first activity after sorting, because it has the shortest time finishing time actually. So in this order, in this way, you can select, you can arrange the activities, then you can select the activity. You have to select the criteria in such a way that is no two activities must be interfering each other. So very simple judgment, we will judge where the first activity completes its execution. So from the end time or the finishing time, another activity may start. So in this way, A2 finishes at slot 3 or the time 3. So A3 can start from time 3 and ends at here as per the data given 4. So A1 cannot be accepted because A1 books the slot from 1 to 5. So there will be an interference. But A4 is accepted because A3 releases at 4. So A4 can start from 4. So once A4 is taken, A5 cannot be taken because A4 books the slot from 4 to 6. But A5 wants to start from 5. So there is an interference. In this way, some activities will be rejected, some activity will be accepted. So here our objective is not only schedule the activity, but the number of activity should be a good number, or more number of activity should be selected. So from this, we are just deciding the making the algorithm or implementing the algorithm. Two parameters, S and F. S and F looks like an ordinary variable, but they are actually one-dimensional array. S stores all starting times of the activities. So it's basically a collection of starting times. F stores the finishing times of all activities. So it is also an array. So first activity should be placed in the A list. A list is final list, and pre holds the index of the recently scheduled activity at any time. So the index of the first activity should be placed under pre. So you have remaining activity from activity 2 up to activity n. So pick up the activity once at a time, identify its starting time, that is S of I, check whether it is greater than or equals to recently scheduled activity, that is F of pre. F is the finishing time of the recently scheduled activity. If it is true, then you append I to the A list and update the pre as the current value of I. Then you continue the process unless and until all activities have been covered. And finally, you return A list. A list will finally give you the list of all activities. So please go through this lecture. If you have any doubt, you can make into the comment section. So let me now stop the recording.